Hello, it's Keith here, and this is lesson 71 of the platform-specific series of my Z80 assembly programming tutorials. Today we're looking at sound on the Elan Enterprise. Now, we did do this before. I wrote a simple sound driver called ChibiSound. It was a driver that took a single byte parameter and it gave a variety of noises and tone effects for simple games. Now, I'm creating a new updated version called ChibiSound Pro. The Pro moniker is a bit of a joke. It's a just slightly improved version. Basically, whereas ChibiSound was designed for simple beeps, ChibiSound Pro is designed for simple music. So we're now passing a total of 4 bytes parameters in 3 parameters. A 1 byte channel number with a single bit for the noise on and off, a 1 byte volume 0 to 255 with 0 being the lowest and 255 being loudest, and a pitch with 0 being the lowest pitch, lowest frequency, and 65535 being the highest frequency for dogs listening or something. And so we're going to be writing this and we're going to be using that to create some multi-platform music. That's the hope anyway. Now, how does sound on the Elan Enterprise work? Well, it works something like this. Basically, we have a series of numbered ports here, and we can write bytes to those, and that will configure the various channels. Now, basically, we have 3 tone channels, 0, 1, and 2. We have 1 noise channel. These are actually stereo. We have left and right volume settings independently, although ChibiSound Pro is actually still a mono sound system. The vast majority of systems I'm programming for are only mono or have fixed channel positions, so stereo volumes wasn't really appropriate. Now, the interesting thing with the noise, though, is we only have a single noise channel. Now, ChibiSound Pro is designed to support ideally 3 or more channels, and they're all intended to have their own noise capability, but this system isn't capable of that, so we'll be remapping any noise enabled functions to the the dedicated noise channel. The problem is, though, the frequency is actually not really very controllable. The only way we can control it is to map the noise rate to one of the other channels. So we can set a value of 1 to 3 and select channel 0 to 2, and the frequency bytes, the 12-bit frequency that we set that channel to will actually then define the frequency of the noise. And so that is what we're going to be doing to get a wide range of frequencies of noise for drum and cymbal effects and things like that. Okay, so that's sort of the concept in a very rushed description. Now, what we're going to do is we're going to go over and we're going to hear some sound examples, and then we're going to look at the source code for the driver, and I'm going to show you how it's been coded to work with this system. Okay, so let's turn on the oscilloscope here. There we go, we've got an oscilloscope, and let's try the ChibiSound Pro test routine. And this is my testing and sound matching routine. So basically, this is what I used to get the driver initially working, check it worked okay, and also to create the lookup table for the frequencies. So you can hear a frequency play now, and it's represented on the screen. And then if I use my joypad, you can hear as I change the number, the frequency changes accordingly. And if I press the fire button, you can hear that I'm able to turn the distortion effect on and off as well. So this is what I used to basically just test the driver. The main purpose of this was for my so-called ChibiTracks software. So if we just fire this up here, and then we run this, and this will play the Chibi Akuma's theme, which was originally written in Arcos Tracker, but I ported it to my own Chibi Tracker Pro, and then I exported it as a binary for the Amstrad CPC, but that same exported binary will play for the Enterprise and any other system in my tutorials, even the ones that aren't on Z80 systems, so the 68000, which is a big Indian system, will play the same compiled binary as exported for the 8-bit systems on the Z80. Now, the song won't sound exactly the same on every system, of course, because of the technical differences in the sound of the systems, but it will at least play, and it will have the same kind of feel and hopefully sound pretty similar. So what we're going to do today is we are going to look at the ChibiSound Pro driver on the Enterprise. The first thing you'll see here is this octave table. Now, this is used to match the sounds, because when we run ChibiSound Pro, we pass the HL and DE pair, and the DE pair is the pitch. And while 0 is the lowest pitch and 65535 is the highest pitch, they won't match the same notes. And so the way we solve this is we have a lookup table of the notes in the octave, and when we want a note like C, we would just look up one of these values here, and if we want an A sharp or something, we would take 2 of the values, add them together and divide by 2 to get the sharps and flats as we require. So that is how we are getting the tones for the music. Now, when it comes to actually setting the sounds, we use the ChibiSound Pro set routine here. And when we run this, we will have HL and DE passing the volume, channel number, and L is also the top bit is the noise on and off, and DE is our pitch. So the first thing we're going to do is we're going to remap the channel numbers, because we could be passed in theory a value from 0 to 127 as our channel number. We don't have that many channels. So what we're going to do is we're going to remap them to a value of 0, 1 or 2, which is far more appropriate for this system, which has 3 tone channels. So that's what we're doing with this. We also have a noise set of bytes here. This is to map the noise state for those virtual channels, because the ChibiSound Pro driver intends that the hardware will be capable of turning noise on and off for each channel. However, this hardware only has a single noise channel. So we're going to remap when we're asked, for example, to turn noise on channel 1. We're going to map that we've marked the noise on channel 1, and we enable the actual noise channel 3. And then if channel 1 later is asked to play with the noise off, we will see that it was previously on, and then we will turn the noise channel off. So that's what the channel noise lookup here is for. There's a few bytes for that. So the first thing we're doing here is we're getting the current noise state and we're backing it up in C, and then we are remapping the channel numbers based on that channel map, and we're storing the channel number back into L with the top bit kept to the same as it was. Now what we're going to do next is we're going to check the previous noise state for that channel. We're going to load the noise bytes there, and we're going to get the offset. There's only going to be 4 entries in there for the 3 channels, and basically we are going to set BC to point to the flag for the noise. Then we're going to check if the noise is currently on. If the noise is currently on, then we're going to set that flag to 1. So we're going to redirect the volume to channel 3. Channels 0, 1 and 2 are tone channels, but what is effectively channel 3, the third channel along in this, is the noise channels. So we are changing L to point to channel 3 there. So we're going to set the volume for the noise channel. We're then setting the noise channel to get its frequency from tone channel 2. The 3 there is tone channel 2, a 1 would be tone channel 0. That is setting this value here, and we're setting those N bits there, and so 1 to 3 is channel 0 to 2 there. So that's what we're doing there. And then what we're doing here is we're shifting the bits of the frequency just to make them a bit more appropriate, to make the noise more accurately match the tones. We're then going to skip over the next part because we're ready to set the volume. If the noise was previously off though, we're now going to check that noise bit which is being pointed to in BC, which was loaded in from the channel noise. And what we're basically checking is to see if the noise was previously on and it's now turned off. Now if it was on before and it is now off, what we need to do is we need to silence the noise, and the way we do that is we set its volumes to 0. So AB and AF need to be set to 0, so the volumes are going to be set to 0. There's 2 because it's the left and the right channel. So we're setting the volume to 0 here, and that is effectively silencing the noise there. And then in either case, whether we've got noise on or off, we're now going to set the volume. So what we're doing here is we're getting the 2 bits of our channel number, and we're adding that to A8 because our volumes start from A8, as you can see, with the left channels first and then the right channels. So then what we're doing is we're getting the 6 bits of volume we can use, because we only want a 6-bit volume for this system, and we're setting the left channel there basically, and then we're adding 4 to the port number, and we're setting the right channel because the right channels are 4 along from the left channels there. So that's what we're doing there. We're setting the left and right channels separately. Now once we've done that, we're then checking our noise bit again, because next we're going to set the frequency. And while we need to set the volume of the noise to the noise channel, that's this channel here, we actually want to remap the frequency to whatever channel we set the noise channel frequency bits to. And so we specified we're going to use channel 2 for our noise, and so what we're doing here is we're setting L so that that goes to channel 2. And that's what we're doing here. We're getting the channel number. We are calculating that as a pair of ports. So the first port will be based on A0, so A0 and A1 for channel 0, A2 and A3 for channel 1, A4 and A5 for channel 2, and of course there's none for the noise channel, which is why we did that remap there. Now what we're going to basically do is we are going to take all of the bits. We've got 16 bits passed to us, but we can only use 12, so we're shifting the bits, shifting them basically into these positions here. And then we are loading the L bit here. We're flipping the bits of it and we're outputting that to the first port, and then we're incrementing the port number. So we would have written to A0, A2 or A4 there, the L part. And then what we're going to do next is we are going to flip the bits of the high nibble. There's only one nibble, and we're outputting that to the following port there. So that's setting the frequency for the high part. And at that point, we're actually done. And you just got a quick summary there of the various various ports there, in case you want to sort of look over this code. So there we go. So that's actually all there is to this system. It's pretty straightforward. It's a nice nice system. The Enterprise is a little bit odd in the sense that it seems to have its own completely different sound hardware to every other system. A lot of systems share things like the AY sound chip. The Enterprise has come up with its own thing, but it's actually very good. It's perfectly capable, and the stereo sound is impressive. It's just a shame I didn't use it because, as I say, so few systems support that. Anyway, go to my website, down the source code and build scripts, have a go with it yourself. You can get the Chibi Tracker Pro as well, which is my Windows-based C# music software. Anyway, I hope you've enjoyed what you've seen today. Thanks for watching, and goodbye.